In this video, we're going to take a look at volcanic activity at three different main types of locations: the plate margins, which will be mostly a constructive and destructive, and something called hotspots, which we'll take a wee look at as we go through. So we start off with a layer with the plate, or with the volcanoes turned on, to see if you can see any patterns here first of all. So can you see any linear patterns? Can you see any clusters? Well, of course, there's a couple of those. There is this linear pattern. Hopefully by now you're really picking up a good spatial sense of where these things are around the world. So that's your Pacific Ring of Fire. You're going to see a linear pattern down here. Hopefully you know where this is, your East African Rift Valley. You're also seeing little clusters like here and here. And some clusters here and things like that. So there is an underlying pattern that helps to explain all of those. So let's start off by turning on the tectonic plate boundaries. It's come as no surprise to you that most of the world's volcanoes are occurring on or near plate boundaries, particularly the linear ones, because the plate boundaries tend to be very linear. Particularly, do you notice here, the Pacific Ring of Fire? I guess the clue is in the name. A lot fewer volcanoes up the mid-ocean ridge in the mid-Atlantic and around the mid-ocean ridges here, however. And then you do have these strange clusters of volcanoes, particularly apparent here in Hawaii, which are way, thousands of kilometers away from the nearest plate margin. Okay, first of all, let's go into the volcanoes and we'll add a filter here because I want to look first of all at a type of volcano called composite. Let's apply that. Turn on the key and we can have a look. So the GIS has now drawn down all the composite volcanoes, which are these ones in yellow. Now, if I turn that off and on, your question is, what type of plate margin are the composite volcanoes mostly found at? Let me actually turn on the key for you so you can see those, and I'll turn that off and on. What type of colour? Well, they're mostly at the green, aren't they? Which are your converging, coming together, which we call and refer to our destructive plate margins. Now again, that should come as no surprise to you based on what you know, but let's go in and take a little bit more look at one or two particular examples of these. So we start off with one that we've been to before, the Aleutian Islands, Pyre Peak. So let's just zoom out a little bit and remind ourselves exactly where we are in the world for this. The Aleutian Islands in Alaska, and here in Pyre Peak. Let's come in and have a closer look again at that. Now, we've had a look at this before, and we know that this island is part of this island arc ocean trench. Pacific plate, or oceanic plate meeting oceanic plate, and we can see very much the volcanic activity taking place here. But let's have a wee look at a few more details about this volcanic eruption. This is a composite volcano. So the last time that this erupted was in the early 1990s, and this island is uninhabited, so it was spotted by some Coast Guard pilots who were reporting the ash cloud going up. You can see the ash clouds. So 1,200 meters above it, there were a few other ash clouds and things coming out, some of them reaching up as high as 3,000 meters into the sky. And in addition to that, you have your lava flow coming down here, and you can see the lava flow coming down to this point. Now, a relatively small eruption, but I want you to notice there you've got your ash and you've got your lava. That's going to be important for some of the things we see in some of these other volcanoes. So there you go. There is an ocean lithosphere, ocean plate meeting ocean plate at the Aleutian Islands. Now let's go to our next one, which is a very famous volcano, Mount St. Helens. You should know where in the world this is. So can you picture it? Let's zoom out and see if you're right. Here we are, northwest United States of America in Washington State. And I'll just click the bookmark to go back into this again. Mount St. Helens. Let's have a good close look at this. This is your destructive plate margin, or is a composite volcano as well. So I want you to notice something. We talked before about this volcanic eruption being very, very explosive. The whole side of the volcano collapsing away, and you had this blast wave coming out, which even all these years later, you can see the devastation that still remains of the trees that were knocked down. Other things that are coming out from here, you can see these mud flows that are coming down the river because this was topped in ice and snow, and it melted to produce these devastating lahars, as they're called, mud flows that travel very, very far away. So that's a very good example of your destructive or your composite volcano. Let's just check the height here. It's 2,549 meters high. Okay, so that's a good example. This very, very powerful, destructive, explosive volcanic eruption. But let's draw some general points about the kind of volcanicity that occurs at these destructive plate margins. Well, first of all, how do we produce our magma? Because, as you remember, the asthenosphere is solid but ductile, the lithosphere is solid and brittle, so you need to produce magma, and in this case it's the hydration melting. The seawater seeping into the ocean plate as it sits in the bottom of the ocean means that as it subducts down in, it brings some of that seawater in with it. The seawater then acts as a catalyst and lowers the melting point of the surrounding asthenosphere, and that produces partial melting. In this case, it produces what is called andesitic magma. Now, that word may seem a little bit odd and strange, but if you think of the Andes, the mountain range of the Andes, where you get a lot of these composite volcanoes, these are magma that is associated with the Andes, so it's andesitic magma. Now, very important for you to know that that magma is extremely viscous. It's very, very sticky. It doesn't flow well, and that means that the gases are trapped in the magma. That's part of the reason why it's so explosive in nature. And then the magma is less dense in the surrounding asthenosphere. It rises up, forms a magma chamber, and can erupt at the surface, producing the composite volcanoes. Now, let's talk about the nature of the eruptions. As I've just said, it's viscous lava, so the gases are trapped, and that produces your volcanic eruptions. So you're getting your lava coming out, but you're also getting some of these other materials. Now, you might remember these from GCSE. We'll pick up on these in the next topic on the volcanic hazards, and we'll go into those in a lot more gruesome detail. Also, these tend to be less frequent eruptions, so the magma is stored for a while and then it explodes in a much more explosive and catastrophic manner. Now, the form of the volcano is partly influenced by the nature of the eruption as well. Whenever this volcano erupts, the first things that come out of it are your ash and your pyroclasts, which are basically your fragmented, very glassy bits of lava that have exploded. You get your volcanic bombs coming out. So your ash cloud will go up and your pyroclastic flow. That's where the stage of the eruption, whenever there's still a lot of gas in it and it's erupting out in a very, very explosive manner. Then the second stage is lava, as the gas has now escaped. So that's going to give you composite layers. It's composed of different layers of some of the pyroclasts and ash, and then lava on top. Then the next eruption, pyroclasts and ash and lava on top. And it builds up and up and up over time with those alternating layers. Because the magma and the lava is more viscous, it doesn't flow as well. So you get a very steep-sided, very classic cone-shaped volcano. So let's go back in here and we'll see that just in action there. You can see that the height of this, as we said again, was, let's click on here, 2,500 meters. But if I just do a quick width measurement here, and we'll compare this to another volcanic type later, it's just about 8 kilometers across. It's not very wide. It's a steep-sided volcano. Okay, let's go and take a look at another example of a zoom in here to Pinatubo, another example of a composite volcano. Here it is, Pinatubo. The elevation here is only about 1,500 meters, not a very, very tall volcano. And again, if we take a wee look at the width of it here, again measured in a few tens of kilometers wide. But let's turn on this hazards here. We'll see what came out of this volcano. Again, we'll pop on the key. You can see here you've got your ash coming out of it. You have got your pyroclastic flows, and you've got your lahars travelling further. Now, as I say, in our next topic, we'll be exploring these in a lot more detail, but you may remember from GCSE having come across those, the pyroclastic flows, which are more dense and flow down the side of the mountain. Not surprisingly, they're going to go down through the river valleys here, so you get a more linear pattern with those. Do you really get a sense of the explosive and destructive nature of the volcanic eruption? This is going to be our case study later on as well, so we'll get a chance to look at that in a lot more detail at that stage. Okay, so that's our destructive plate margins. Pardon me, where you get your composite volcanoes. Let's go and take a look at your constructive plate margins. We'll zoom out a little bit here so we can see where we are, and then you go back down to the world volcanoes, and I'm going to remove the filter. And so we've got all the volcanoes on again. Now we can definitely see here that most of those composite volcanoes are along these destructive plate margins. There's the Andes giving us the name, the andesitic magma. But if you come here to the constructive plate margins, you can see that there aren't anywhere near as many volcanoes. Now, does that mean that the constructive plate margins are much quieter in terms of volcanic activity? Well, it turns out no, because about 75% of all volcanic eruptive activity takes place along the constructive plate margins. But it tends to be of a very different nature. Let's go in and have a closer look at what goes on here. So we get most of the eruptive activity takes place here, produces these pillow lavas, right? So let's remind ourselves again of what it is that produces the magma. In this case, because it's a constructive plate margin, you've got the heated rock rising through convection in the asthenosphere, and as it rises, the pressure falls. That gives you your partial melting, produces your magma, which is less dense in the surrounding asthenosphere, will rise up and form a magma chamber, and then come up through cracks and fractures in the ground towards the surface. Now, the nature of the eruptions here, the way in which the magma is produced here produces what's called basaltic magma. It's much less viscous, so there are very few gases are trapped in it. Because the gases are trapped, then the eruptions tend to be quieter, forming pillow lavas. We'll take a look at this in a moment. And they tend to be more frequent. So you get a lot of frequent, quieter eruptions producing a lot of this basaltic lava flowing across the surface. 75% of the world's volcanic activity occurs in locations like this. So what's the form of the volcanic activity? So we've seen here the magma rising into the magma chamber, and then it comes up through these vertical dikes or intrusions into the ground, and as it comes up towards the surface, it then erupts at the surface. Now, the way in which it erupts comes out into the surface, and because it immediately hits the sea, the surface of it is cooled very quickly, and you get the skin forming on top of it. And as the skin forms, then the rest of the lava inside it kind of still moves forward, and you get these lobes, this tongue-shaped lobes forming, and eventually the surface of it hardens enough to constrain it, and another bit breaks out, and you get this series of these lobe-shaped features being produced in this pillow lava. So this is very much one of the main processes that produces the new seafloor. As part of this process is seafloor spreading, generating the seafloor across that 70,000 kilometre long ridge that runs around through the major oceans of the planet. So that's why you get most of the world's volcanic activity occurring here quietly, where nobody can see it, and it doesn't really harm anybody, get in anybody's way. Okay, let's move on then to our third type. Pardon me, and this is over here in Hawaii. Now we're looking at Hawaii because, if you will remember, it's a very good example of that little cluster of volcanoes that is found thousands of kilometres away from the nearest plate margin. If we measure that, there you go, nearly 6,000 kilometres away from the nearest plate margin, and yet you've got some volcanic activity there. Now, if we turn on the legend here for the type, you can see that it is mostly made up of shield volcanoes. It's a different type of volcano. Hopefully you remember those from your GCSE days. That's your shield volcano. Now, let's have a little bit of an observation of the pattern that we can see here. There is your initial island with your volcanoes. Now, what can you see in terms of the pattern? Can you see another linear pattern? In fact, if I zoom out, I've drawn it on here, you can see a linear pattern of submarine islands known as seamounts. Go all the way up here to this destructive plate margin. There you go. We can follow them all the way back down here to Hawaii. So again, anytime there's a linear pattern, there seems to be some kind of hint or clue about what's going on. Now, talking of clues, let me give you a few clues about what's happening here along this section of the world. So you've got, first of all, the newest, largest islands here with active volcanoes. Then as you move here, the islands get smaller with fewer volcanoes. The further and further away, the islands not only get smaller, but actually have been eroded down underneath the sea. Now, you can already work out that if these have been eroded more, they must have been around for more, so they must be older islands. You can date them as well. These are older islands. So as distance from the big island here in Hawaii increases, the age of the islands increases. So you've got a linear pattern, you have got a change in size and age, and you've got a clustering of the volcanic activity there. I wonder, can you figure out what might have produced this? Pause the video and see if you can work that out. Okay, I'm just going to give you one more clue, and that is our tectonic setting. And for that, we need to zoom all the way out here to see where we are in totality. And I'm going to turn the volcanoes off so you can see the plate boundaries a little bit better. There's Hawaii, don't forget. So the tectonic setting of the Pacific Ocean, which hopefully you're really picking up by now. You've got constructive margin here, and you've got destructive margins to the north and to the west. And what that means is that the ocean floor is being created here, new sea floor created here, and it's slowly moving over those tens of thousands of kilometers over a time scale of, a couple of 100 million years, traveling in a conveyor belt style across here. Now, I wonder, does that give you a little bit more of a clue? Because if it's traveling from here to here, look at that pattern of the islands. The volcanic pattern is there. Now, if you think about the direction that the plate is moving, I wonder, can you figure out what's going on? So we've got the direction of plate movement. We have got the volcanoes located there. And we've got older and smaller, more eroded islands the further away you move. What is going on? So, let me explain to you. We'll go down here. This one. So if I zoom in a little bit more, you can see the volcanic activity that's taking place. There's Mauna Loa, there's the crater or caldera across the top of it, and there's all the lava flows coming out. But let me click on my little link here, and I'll explain to you what's going on. So here is Mauna Loa. Here's a look at it from the side. You can see that it's very, very different in form to the composite volcanoes, which were quite narrow and quite cone-shaped. This is much, much more broadly based. But what are the processes that are forming this? Well, basically, this is formed above what's called a hotspot. Now, a hotspot is like a mantle plume, so it's like an area of convection where you're getting the hot rock in, or the heated rock in the asthenosphere is rising up, and it rises up, but just in this one spot. So unlike, if I zoom out here, unlike the convection up here at the spreading ridge, at the constructor plate margins, which are forming this linear pattern, at a hot spot, you're just getting the convection rising up at that one point in that one location. So the hot spot basically stays put over that time scale of tens to hundreds of millions of years, and then the plate is moving across the top of it. So what happens is that whenever the plate is above this mantle plume, you get this decompression melting occurring as it rises, forming the magma chamber, and then you get this active eruptive volcano producing the island. Initially it will form under the sea, and then it will come up above to produce the volcano itself and the island itself. Then over time the plume stays static, but the plate moves away, and this island moves away from the active hotspot. You'll get a little bit of the plume dragged across as the plate moves, which means you might get a little bit of volcanic activity here, but you're getting erosion beginning to occur and the island becoming smaller. Again, as the plate is moved further away, this island then is moved away from the influence of the plume entirely, and you get no more active volcanism. The volcano there is extinct and the island gets eroded. That keeps going, no more active volcanism, but the island gets eroded further and further until it becomes submerged underneath the sea level, and you get these flat-topped, what are called seamounts under the sea. So you get this linear pattern here with the active volcanoes found at one end clustering here, and as you move along here the islands get older and smaller. This is exactly what we saw operating here. We go back into this. There is our active volcanoes there, and as you move away the island get older and smaller in that linear pattern. Now let's think a little bit again about the nature of the eruption here, because as we discovered last time, this is going to produce basaltic magma, and if you remember, the basaltic magma is less viscous, fewer gas is trapped, so it tends to be less explosive eruptions, and you get your different layers of lava, and you tend to get very frequent eruptions. And because it's less viscous, it's going to travel really, really far, which gives you this really gently sloping shield shape. So the slope here at Mauna Loa is about 12 degrees. It's very, very gentle. And if we go in here to the GIS map, I will click on Hawaii close up again, and we'll come in, we'll have a much closer look at Mauna Loa. There it is. Let's get a wee bit of a sense of the scale of this one. So I'll turn on the world volcanoes again. So the height of it is 4,170 meters. So it's a really, really tall mountain. But look at the diameter of it. If we get our measure tool this time, and we go, now if you remember, Mount St. Helens was about 20 kilometers, but you can actually measure this one all the way down here. It's much, much wider, much, much broader. So that gives you our shape here that we've seen, that it is much, much wider and much more gently sloping. Now at 4.2 kilometers high, this is a very, very tall mountain indeed. I wonder how it rates though to the highest point above sea level on the planet, which of course is Everest. It's 8.8 kilometers. So you can see that this is much, much smaller than Everest. It's half the size of Everest. But if I turn on this, it maybe makes this a little bit clearer for you. It depends really on where you measure this from, because as you can see, this has built up from the ocean floor, and you can see that this mountain goes all the way down to the ocean floor. So if you measure the height not just from sea level to the top, but from the ocean floor to the top, you get a height actually of 10.2 kilometers. So in terms of the actual physical size from the base to the top, this mountain is bigger than Everest. It's not as high above sea level as Everest is, but it is a bigger mountain that size. It just gives you a sense of the real scale and size of this as a volcano. Absolutely incredible in size. In fact, this mountain is so big that the sheer weight of it actually compresses the lithosphere down a little bit, just above the mantle plume. And as you move away, as the islands get eroded down a little bit, then you get this rebound a little bit as it comes back up again. So this will just remind you of some of your isostatic reasons for sea level change. Okay, let's take a look at a few more examples of some of these processes from hotspots. In fact, let me just zoom out actually, and we'll turn on the world hotspots here. Let's see if I turn off the world volcanoes for a moment. You can just see how many of hotspots. There's the one in Hawaii. You can see where these are. Now look at the pattern. They do tend to be a lot more random. You get them both under the sea and a few under the land as well. And they're certainly not concentrated around the plate margins, although you do get some of them along plate margins as well. Let's go and take a look at another example. I'll just turn selected hotspots on here for us to visit and the volcanoes back on, and let me go into Easter Island. Okay, so again you can see there's the pattern, and there is a volcano there with this linear pattern of these seamounts, the islands now that are underneath the ocean. Turn on the ocean base, you'll see that maybe a little bit more clearly. It's pretty clear without it anyway. Let's go and have a look. This is Easter Island. Now, Easter Island's very famous because of the statues that appear there, but we're going to take a look here at the volcano. You can see that it is a shield volcano. Let's have a look at this photograph because I think this is pretty cool. So what you have here is the Rio Cow crater on Easter Island. The edge of that ridge that I looked at, which is about 3,800 kilometers long. Now this is no longer above an active hotspot. The active volcanicity is about 100 kilometers to the way. I'll show you in a moment the seamount that's coming up there. Underneath the ocean, it's forming the next island. But you can see here this amazing crater. It's got its own little kind of microclimate in here, and you get a lot of the kinds of farming and so forth that take place in the island at that point. So there's the island, and there's your 3,800 kilometer ridge there of those seamounts that are formed. And this map shows you exactly the age. So what you've got here is a spreading ridge, constructor plate margin. You've got a subducting plate, destructive plate margin here. So the plate is moving from here to here, and the hotspot is staying here. So as the plate moves over the top of it, as you move further away, there's this linear pattern of age increasing and the islands then being eroded and going under the water. Okay, next little example of this, we're going to go to Galapagos. Famous because Darwin visited. So again, what you should be able to see here is our seamounts there, the raised portion of the seafloor a little bit here, but you can see all of these volcanic islands in operation here. This is an amazing set of volcanic islands here. So you can see a whole bunch of composite volcanoes, or sorry, shield volcanoes in red, those little red triangles there, forming these islands with these large calderas and craters along the top. If you have a wee look at the size of that. So that crater there is nearly the same size as the Power Peak volcano that we looked at up at the Aleutian Islands. So these are much, much broader volcanoes than your composite volcanoes would be. So let's take a wee look here. Where's my link? My graphic. Maybe I need to turn that on. So let's zoom in. We'll have a wee look at this. Can open this up in a new tab here, and here we go. Right, so here we have this very, very classic shape of your shield volcano. Now you're getting an eruption here throwing some ash up out into the sky, but this is a quieter eruption than you would get in the likes of Mount St. Helens. This is now here we go with some Spanish. This is embarrassing. I did French at school. I'm quite good at French, but la cumbra. Is that what it is? I do apologize for those of you who speak Spanish. But this is the volcano here on the island of Fernandina. It's still forming, and this volcano is one of the most active volcanoes in the world. If we zoom in closer, here you can see the less viscous lava that's coming down here. It's a relatively gentle eruption, as you can see, and the lava is traveling quite far down these gentle slopes. there's that volcano in the background, and you can see the relatively gentle slopes there along these. Now these are called cinder volcanoes. This one has been eroded a little bit, made just of pulverized rock that came out. Another type of volcano we're not really going to worry too much about, but it does look absolutely beautiful there. Okay, we're just going to take a look at one more ocean hotspot here, and this one is quite interesting. This is Tristan da Cunha, which is a volcanic island in the middle of the Atlantic Ocean. But this time, you've got two linear patterns here of your islands and seamounts running across the oceans from the center of the Atlantic Ocean here. Now, this is not only a linear pattern, but it's symmetrical again. So I wonder, can you figure out what might have been going on here? If I zoom out a little bit to give you the context, there's one linear pattern of seamounts, there's the other linear pattern of seamounts. What do you think has happened here? Well, there's Tristan da Cunha, right, volcanic island. Let's have a closer look at how it actually formed. If you thought that this was formed as the Atlantic Ocean spread apart, you're absolutely right, because this is sitting above the Walvis hotspot, and this is one of the hotspots that drove the seafloor spreading process that caused the formation of the Atlantic Ocean. You can see here that the volcanic rocks here in South America and in Africa were formed at this stage as well. But what has happened is Africa's moved away, South America's moved away, the hotspot has stayed put, where the seafloor spreading has occurred above and the continents have moved further away. So as it moved further away, as these were sitting above the hotspot, some of these volcanic islands were formed here, then moved further away. At the same time they formed here and then moved further away and further away and further away and further away and so on. So you basically get this symmetrical pattern because of the hotspot sitting close to the mid-ocean ridge here, causing the volcanic islands either side. So there you can see that symmetric pattern either side as they move ahead or move away. One final quick point here. This is an inhabited island, Tristan da Cunha. This is Edinburgh of the Seven Seas, and it has the wonderful honour of being the most remote settlement in the world. The next nearest settlement is on St Helena, which is over 2,000 kilometres away. There's no airport here, you can only get in and out by boat. It must be incredibly remote, and just so you can see, here's an active volcano, or volcanic flow that came down here and threatened this settlement, I think in the 1980s, and there's the lava flow that came down here towards it. Okay, so let's zoom out and recap on where we've been so far. So we've seen that most of the volcanoes in the world are around your destructive plate margins in the Pacific Ocean, and they tend to be your composite volcanoes. We've discovered that there aren't many volcanoes on the constructive plate margins, and yet 75% of the world's volcanic activity occurs there, because that's mostly a very quiet pillow lava eruption. And we've noticed some of these hotspots, these locations where you get these little volcanic islands all over the place. Just notice here, just because we're here, there's Tenerife. Have you ever been to Tenerife? Tenerife sits above a hotspot as well. These volcanic islands are formed by that. But what about hotspots underneath the continent? Because there are some examples of those. What do they look like? So we're going to go first of all to a region that we've gone to before, which is your East African Ridge Valley. As you know, this is an area of active volcanism. And again, what's driving this, because you're not officially at a plate margin yet, but what's driving this is some hotspot activity here. So if we go in and have a look at the Arfar hotspot, which is down here, there it is, and moving at a rate of 16 millimeters per year. And we can see some of the volcanic activity that is going on here at this location. So Erd Ali, open this in a new tab, we'll take a wee look at this. This is in the Danakil Depression, an area in the Central Rift Valley where it's coming down. But you can see this volcano, and it's definitely not a composite volcano, because look how flat it is. You get these massive craters here in the midst of this area, which is showing how volcanically active this is. Let's get a little bit of a reminder of the context of this. So we have a look here. Now these maps, this is the newest one, this is going back in time. So if we start off here, there is the Arabian Peninsula, there's Africa, and there is your Gulf of Aden and your Red Sea. This is the current situation, and then there's the Afar region going down into the East African Rift Valley. Okay, but if we rewind about 35 million years or so, before the Gulf of Aden and the Red Sea opened, what you have here in these areas that are now sea, you have something very similar to what's happening in East Africa at the moment. So that rifting process opened up these linear seas, and if we go ahead in time, that rifting process here will open up those linear seas as well. So you can see the hotspots here are partly responsible for starting to split apart the continents. But the next hotspot we're going to go to is one of the most famous ones in the world. That's continental hotspot because it sits underneath the Yellowstone National Park. Now I want you to notice the pattern here of volcanoes. Can you see a bit of a linear pattern here as well? But let's go in first of all to take a wee look at Yellowstone National Park. Yellowstone National Park, there is, if you remember from GCSE, there is your caldera, right, your massive big caldera. Let's just get a sense of the scale of this across there. It's something like 50 kilometers across, but if you measure from this location to this location, 70 kilometers across. This is a massive big caldera, and we'll get a wee bit of a sense here of just how volcanically active it is. If I click on this, we know that there is heat escaping here from the ground because you get these geysers coming up. This is Old Faithful, the superheated water coming out. When you come over here, you'll see this, the Grand Prismatic Spring, which is the largest hot spring in North America, and it is temperature of around about 70 degrees C. A lot of the minerals coming out here, and the bacteria that are feeding on the minerals and forming on them give this a vivid colour, and you can see the steam coming off. Now there's a person down there, so just to give you that sense of scale of how big that is. So it's a very tectonically active location indeed. But if we zoom out, you'll see that this is a volcanically active region that is far away from the nearest plate margin. Here's your destructive plate margin, so how far away are we from it? Let's use our measure tool to get a bit of an idea. We are over 1,000 kilometers away. You can see the Cascade region here, that are these composite volcanoes that are formed by your subduction. Down underneath here are only around about 200 kilometers away. So this is well beyond the subduction zone. So what is it that's causing the volcanic activity here? Well, we already know, don't we? That's the hotspot. Now, here's something. Whenever we were having a look over here at Hawaii, we discovered that there was a linear pattern here, where the active volcanoes were clustered at one end, formed because the plate was moving over the static hotspot. The hotspot stayed put. The plate moved from here up here, passed over the hotspot, an island was formed, and the islands moved further away towards the destructive plate margin here. So I wonder, can we see anything similar in the case of Yellowstone? Okay, so what I want you to look out for here are these. Let's just get rid of this, tidy this up a little bit here. Because what I'm going to do now is to show you a hotspot time track. I'm going to show you the evidence that we've been able to find of former calderas and former massive volcanoes that formed in a linear pattern across here. Now this is time enabled, so we're going to see how these move over time. Okay, so let's press play and see them move. Now you'll see that pattern, right, as they're moving across during the process here. Now, we go up to the present day. Right, if I drag this back across and then reveal all of them, you can see this linear pattern of volcanoes with the active area of volcanicity here. These ones aren't active anymore. The active area of volcanicity is here. That looks extremely similar to the situation that we had in Hawaii, doesn't it? So what you've got here is a static hotspot, and you've got a plate moving over the top of it. So my question is, what's the direction of plate movement here? Is the plate moving from the southeast to the north, or from the southwest to the northeast, or from the northeast to the southwest? What direction of plate movement would produce that? Let's zoom out and remind ourselves of the context here. What you've got is this plate spreading apart here. You've got seafloor spreading, which is pushing the plate in this direction. So that means that the plate is moving from the northeast down towards the southwest. So the hotspot then, this volcano used to be over the hotspots. The oldest volcano used to be over here, but has since been moved away. Again, let's get a sense of the scale and the distance of that. So you're talking something in the region there of 600 kilometers. Okay, let's go in a little bit closer and have a look at the processes that are going to be producing that. Go in here. And so what's the hotspot under the continents? Now, very similarly to before, you've got your mantle plume coming up. So this is your single point of convection rather than the linear pattern you get as your constructor plate margin. And as it rises, partial melting occurs because of a fall in pressure producing magma. But there's something a little bit different here because this is coming up through continental lithosphere. And it melts some of that continental lithosphere, which changes the chemical composition slightly. You've got a much higher silica content, which produces a type of magma which is called rhyolitic magma. If you remember, with the hotspots underneath the ocean, it formed basaltic magma. But this is rhyolitic magma, and one of the things that's characteristic because of the silica in it is highly viscous, and that then gives us our explosive eruptions. Now that's why Yellowstone is a supervolcano. It last erupted 630,000 years ago, producing a supervolcano eruption which created this 70-kilometer wide caldera. So there's the caldera here, and this is the line from A to B, showing you the height of the land, the elevation. And you can see that caldera in there is absolutely massive in size. So here is what's been going on. There's this static hotspot, the mantle plume. There's the plate moving across it. So this volcano here, this caldera, used to be here. It's formed here and moved away. Just one thing to note, that the caldera here above Yellowstone is elevated slightly because of the mantle plume, which makes the lithosphere here hotter and more buoyant, and therefore it rises up. And then as you come down here into the valley, gets lower down again. But you get this linear pattern here of former volcano calderas, that as you move here, they become older, and they become smaller as you move further and further away. Okay, so let's zoom out again and just remind ourselves of where we've been. What we have here is most of the world's volcanoes are found in linear pattern around the destructive plate margins, especially the Pacific Ring of Fire and in here into Asia, those kinds of locations. You do get some volcanoes along the constructive plate margins, but very few. 75% of the volcanic activity of the world occurs along here. However, it is that much quieter pillow lava eruptions that is contributing to seafloor spreading. Then you get your clusters here. These are formed by hotspots, but the cluster reveals actually there's a linear pattern there. The cluster of active volcanoes below the hotspot. The plate moves over the top, and whenever the plate is sitting above the hotspot, that's when you get active volcanoes. When it moves away, the volcanoes become extinct and the volcanoes become eroded down to form the seamounts. You can see them there. You can see them here. You can see them here, Tristan da Cunha, all around the world. You've also got your hotspots that are forming underneath continents here in East African Rift Valley, which is part of the helping the process of seafloor spreading, or the formation of the linear sea, which ultimately will split off the Horn of Africa from the rest of Africa. And you see it here at a hotspot under the continent in Yellowstone. One of the differences between the hotspot here, though, is because it melts some of the continental crust, you get your silica magma, which is much more viscous and much more explosive. Okay, so the last place that we're going to go and pay a little bit of a visit to is Iceland. We definitely have to have a look at Iceland, because Iceland is an extremely volcanic region in the world. We couldn't really look at volcanoes without looking at Iceland. We can see that Iceland does sit at the constructive plate margin, but unlike anywhere else along here, it's a large island that's growing up out of the ocean. Now, there's other places where you get some islands coming up. You can see there's a little hot spot there as well, the Azores. But Iceland is pretty much unique, as in it's a huge island that's sitting on the plate margin, and it is helped, of course, by the hotspot over here over Iceland as well. So you get this combination of the constructive plate margin and the hotspot, the mantle plume rising here, which makes this incredibly volcanically active. You look down here, there are very few volcanoes along the plate margin there, but when you come up to Iceland, you get a lot of them forming here. You can see them all over the island, and you've basically got the plate margin coming through here, and it's slightly more complicated. It splits here a little bit, and you can actually go and stand in the Rift Valley. You can see a little bit of a hint of it there the way through. You can actually go and stand in there if you go and visit Iceland, get a sense of the plates moving apart. But the place that I want to come down to is this little location here, and it is this volcano, a very famous volcano which erupted in 2010. So this was the volcano that got newscasters really flummoxed whenever they were trying to pronounce it all of those times. They've summarized it down here a little bit, so let's get the actual spelling of it. There it is. Can you have a go at pronouncing that? Are you ready for this? I'm going to have a wee go myself. Now, I do apologise for any Icelandic speakers here. That's my best attempt. Which is absolutely mangling it, no doubt. But you will have to learn how to spell it. Thankfully, you'll never have to pronounce it in the exam, but you will have to learn how to spell it. But it is, let's get a bit of a sense here. This is a composite volcano. So the height is about 1,600 meters. Let's get a bit of a sense of this scale, of the width of it. Let's get the measure tool on the go. Why is that not measuring? There we go. So again, not that wide in comparison to the likes of Mauna Loa. Just as a bit of comparison here, this Katla is a shield volcano nearby. Actually not quite as high, but you can see it is much wider than Eyjafjallajökull. There you go. So, but the thing that I want to look at here is a couple of the hazards that came out from this volcanic eruption. So let's open this up. I'll have a bit of a look here. So it triggered what are called jökulhlaup. My Icelandic is rubbish, which is basically the melting of the glacial ice. As you saw here, this is sitting on top, or a glacier is sitting on top of the volcano here. And whenever it erupted, it melted some of the glacial ice, and you got these floodwaters that are produced. These are glacial floodwaters that are produced by volcanic eruptions. So you have a wee look at this. There's Eyjafjallajökull, and what you've got here is your glacier on top, and the active crater melted some of that and caused this jökulhlaup to flow down here. There's a minor one down here as well. It came out really quickly. In fact, this is one of the few places where there's the threat of jökulhlaup in Iceland, where there are places that could be reached within 1 hour of the volcano erupting. So they had to have a very quick response here to this. And particularly in the beginning of the eruption, because the Galapagos had volcanic debris as well as icebergs and was going at a very high velocity, and some of them were very, very hot. So you basically had the river gauges here that were measuring the discharge, and you can see the discharge going up very, very quickly, and also the temperature going up very, very quickly because of the heat from the volcanic eruption, which they were monitoring these, and that allowed them to get the evacuation order in place. The other thing that it produced was this massive ash cloud that went up into the sky. Now, this is going to be a more explosive volcano anyway because it's composite, but it was basically the meltwater went down into the crater and caused the gas then just exploded very, very explosively, and it went up into the sky with this ash cloud. Now, the ash cloud travelled all the way across Europe. You can see here, and the ash cloud being carried here to the southeast by the direction of the winds. This photograph here is very compelling because you can see just how high up into the sky it goes. And then you get this ash cloud that spread over most of Europe, and it grounded a lot of the flights in and around about Europe because this was extremely dangerous to the aircraft, not only when you could see it, but the very, very fine-grained particles going all the way around the sky, causing significant impact and disruption to flights all the way across Europe. So if I zoom out a little bit, I have a layer here which shows that in operation. Just go and find it here. So there we go. Turn that on, and you can just see how much of Europe was affected by that and that ash cloud, including all the way down here to our own little location. So even though the fact that we are, let's see how many kilometers away, 1,200 kilometers away from Eyjafjallajökull, even though we're that far away, still the ash cloud came and affected us, and flights were grounded all over Europe. Okay, so final quick summary, just to make sure that you've seen the overall patterns. We're looking at volcanic activity at the plate margins, your destructive and constructive in particular, and your hotspots. So what we're discovering is that the vast majority of volcanic activity is composite volcanoes at your destructive plate margins, which are mostly around your Pacific Ring of Fire, so Sandwich Islands as well, locations like that, but that's mostly where they are in that linear pattern. There are few volcanoes at your constructive plate margins, but we get 75% of the world's volcanic activity occurring there. That's mostly because that's your quieter pillow lava, which is your basaltic magma, which does not trap the gases and doesn't erode, or doesn't explode, doesn't erupt quite as explosively. Then you've got your hotspots. You can get your hotspots underneath the ocean, which give you your linear pattern of islands getting smaller and some of your seamounts there underneath the ocean because the plate is moving over the top of a static hotspot. You can get other hotspots around the world, including the Yellowstone hotspot here underneath the continent, which tends to be more explosive because it melts some of the continental lithosphere on the way up, increasing the silica content. So that is an overview of the volcanic activity, the different types of volcanic activity at your different plate margins and at various assorted hotspots around our planet.